Then, okay, what's this? This has changed, interesting. Good, then let's start with statistical methods. So, as I said last week when we jumped a little bit into calculus, the general topic until Christmas is Fourier analysis. So, or let's say until 2 weeks before Christmas, because I also want to get to differential equations before Christmas. Oh, sorry. See, I asked you whether there's something. You said there's nothing. But there is something. So, yeah. Great, now we have Mickey Mouse. Yes, that's fine. So the topic is Fourier analysis, and as I said also last week, the thing why I chose this as an entry point this year to statistical methods is because it allows us to review some basic high school mathematics essentially and get you started on the mathematical and scientific thinking once again after your time in your bachelor where you maybe did something else. The way I want to proceed, as I also said, is instead of basically going over step by step all the stuff that you find in PMFN on calculus, sets and functions and so on, I want to basically work using a, if you want, problem-oriented approach. So I will introduce foundations whenever we need them. Yeah. So. And in this kind of setting, we will then continue today. So the first thing that I want to first discuss is kind of the general picture, because now that we know what real valued univariate functions or univariate real valued functions are, we can discuss the general picture of Fourier analysis. And once we've done that, I want to remind you of 3 functions that we will need in the following: the exponential function, the sine function, the cosine function, and then get into Fourier analysis by talking about what I call generalized cosine and sine. And then the first big thing to discuss in terms of Fourier analysis is the real Fourier series. So that's the first major milestone. The stuff until there is kind of preliminary stuff. And when we're talking about the the real Fourier series, we also need to discuss integrals again. Because you cannot get what the coefficients in the real Fourier series are if you don't recall what integrals are. So, but let's start with the general picture so that you have an overall idea of what we are aiming here for with Fourier analysis. So, you know by now that there exist things that are called real univariate real valued functions. And last time I explained what this notation means. Yeah, anyone who wants to explain briefly what this means?
We insert a real value, like a real number.
Mm-hmm.
Into the function, and what we get is also a real number.
Exactly. That's all that this means. Yeah, exactly. And of course, you are familiar with plotting these kind of things. So you know that one can, for example, plot the input arguments on the x-axis and the output arguments on the y-axis. And then you can get something maybe like this. So this is now not a function in terms of how you are used to it with a little formula that provides the function, but it's just something that takes on values over some space. Now, in basic science, or specifically, of course, in neuroimaging and functional neuroimaging, cognitive neuroscience, whatever, one often has these kind of things where, for example, one has on the x-axis something like time, and then one observes something at specific time points, so one time point after the other. For example, the MR signal, so the magnetic resonance imaging signal at a specific location, or the EEG signal in a given electrode, or if you want, also reaction times in a sequence of trials where at each point in time, or at each trial, the participant does something. That's maybe not the best example for what we have in mind. So I think the better example is to think about something like an EEG potential at a given electrode, or an MR signal at a given voxel. So the important thing is that in this case, the function that we look at evolves over time. Another option is that we have something that evolves over space. So if you think about making pictures of the brain, like with the MR machine, of course you have a notion of space that is represented in the picture, and for each location in space you allocate a gray level so that you get a picture, and here we would have a one-dimensional space, and then this might be a gray level evolution. Now this is what one can call, let's call it a time or space domain signal. And this should be fairly familiar to you because you all dealt with functions in school. You did these things called, I don't know what it's called in English actually, Kurvendiskussion, where you find the extreme of functions and so on. So you are familiar with this kind of universal real valued function aspects. Now, a fundamental thing in science and also then in cognitive neuroscience is to look at these kind of signals in what is known as the frequency domain. So what that means is that, again, we have kind of this Cartesian system with an x and a y-axis. But now the fundamental thing is that the x-axis does not encode a notion of time or a notion of space, but a notion of frequency, whatever that is supposed to mean. But for the moment, just be happy with the idea that we have low frequencies here and high frequencies here. And and that's kind of the frequency domain then. And for each frequency to represent exactly the same signal as we see here in the time domain, in the frequency domain one has a measure of frequency amplitude, often also called power, although one needs to be a little bit careful there, but let's call that frequency amplitude. And what one then plots over frequencies is also called a frequency spectrum. So looking at this, I think there's quite some low frequency amplitude in there. So let's maybe have something here. And then there's a little bit of a intermediate frequency if you look at this. So maybe let's have something like this. And then high frequencies are quite low. So that is what is referred to as a signal in the frequency domain. And now the fundamental idea of Fourier analysis and the different things that are associated with Fourier analysis, like Fourier transform, inverse Fourier transform, discrete Fourier transforms, inverse discrete Fourier transforms, and the fast Fourier transform algorithm. The fundamental thing is to be able to switch between a representation of a signal in the time domain and a signal in the frequency domain. Yeah? So that one can either look at a signal this way or can look at a signal this way. And if one has, for example, records a signal this way, one can go back and reconstruct, and that's a fundamental thing in MR, reconstruct a signal in the, in this case, the space domain. So one can, of course, start and ask why? Why? And well, that's actually not that easy to answer. So the where this is originally coming from is actually from the theory of partial differential equations, where what's his name? Fourier, I guess. Was it Fourier? I'm not quite sure. The guy with the heat equation. Was it Fourier? I guess. Needed to actually solve some partial differential equations. Needed to check that one can actually represent a function that is represented over a kind of domain that represents time, in this case actually space, because it was heat equation, it was about cannons and how they cool down or something. Needed to show that one can represent them as essentially a composition of frequencies, whatever that means. So this is where that originally came from, and then another reason to do these kind of things is that certain operations, for example, things like convolution, which we will maybe talk about in January, February, can be done simpler in the frequency domain. So certain mathematical operations on functions are easier if you convert them first to the frequency domain. So this is kind of a good motivation. For what you are doing in functional neuroimaging, the main motivations to look at this are, as I said previously, is that the MR imaging techniques works like that. So in MR imaging, you actually acquire the signal in the frequency domain, which is also called K-space. And based on this, you reconstruct images, so gray level values over space. So that's fundamental to magnetic resonance imaging. So this is where Fourier analysis comes in there. Then there are a lot of people who are interested in frequency responses of the brain. So you might know, so somebody was interested in sleep, you know that there was you, right? Can you tell me your name? Because then I might remember that.
Mary.
Mary, okay. Mary, sleep. Good. That in sleep you have these different sleep stages with different frequency bands, like the delta band and so on. And you know all from psychology that you have like something like alpha 10 Hertz oscillations in the EEG and so on. So there is some interest in looking at EEG data in the frequency domain. There's actually a whole industry of people doing EEG frequency analysis. And looking whether there are differences in different frequency bands evoked or induced by some external stimuli. The motivation, from my perspective, for doing that is not that clear, although they always think that it's very clear. But it exists, so you will come across Fourier analysis also there. And then finally, whenever you do some kind of signal processing, so even if you do EEG analysis without looking at frequency responses, you might employ some filter, and filters have certain cutoffs in terms of frequencies. So it makes a lot of sense to become somewhat fluent in looking at signals and kind of inferring their frequency content. So that's kind of the motivation to look at that. Before I ask you whether you have questions regarding to that, one thing to be emphasized here, what I've shown here right now is kind of a mathematical model thing. So we are talking about functions here, which, although I didn't say it, which I assume to be continuous over space, maybe even differentiable. This is of course not the case when you're really dealing with real data, right? So when you have data in our times, they are usually called digitally, so they are discrete. So what you actually acquire with an MR machine or with EEG, because you have a sampling rate, you acquire these discrete time points and nothing in between. So also this is maybe then not the best representation. What this gives you is also a discrete frequency spectrum. The thing is, although we are interested in data, so we are interested in this discrete case, we will have to talk about the continuous case, because this is actually where the theory is rooted. So it's much easier to talk about discrete Fourier transforms after we talked about continuous Fourier transforms. And then finally, a different perspective on the whole thing is that you can also view this approach as a modeling approach. So if you call this the data, then representing the data in terms of frequencies of different amplitudes is a model for the data. And this model, like any model, and as I said, I would kindly ask you to also watch the GLM lectures. Every model can be fit to data, and the fitting aspect here is actually the fact of evaluating the frequency coefficients. So this whole modeling business with Fourier analysis is not that strong, because traditionally people who do Fourier analysis, they don't think that much in terms of that they model the data. They just think they generate a frequency representation. But if you think more about it, it's actually a model. It's a quite well defined. It's a model that uses some certain aspects to model the data. And this is also why I sometimes don't know why they do that in EEG, because they have this sine cosine model, and I wonder whether that's such an awesome model. Good. Yeah, so that's the general picture. And this is what we are trying to talk about. And now, do you have questions about this general picture? Who is familiar with this? Who has seen something like this before? The rest? No. Nobody has seen kind of that you can look at data in the frequency domain. Never heard of that. Good, then you learned something new. That's awesome. It's a very fundamental technique. So engineer students, so people in engineering, they are really all about Fourier analysis. So that's kind of what they learn in the first in the first year or something. In physics, it's also quite strong. In math, it's more kind of the question of whether you can actually do it, or what are the conditions that you can do Fourier analysis. And in cognitive neuroscience, as I just told you, it features, and we should talk about it. And as I said, you cannot understand magnetic resonance imaging if you don't understand Fourier analysis. Good. That's the general picture. Clear? Questions? No? Good. Too early in the morning? Good. General picture done. Good. then of course this is the general picture, and the question is now, if we want to do it, so if we have some data acquired in the time domain, how does this work? How can we get to this? What does this whole thing here actually mean? So what are frequencies and what does it mean? So maybe you feel like, okay, done, that's Fourier analysis, let's go to the next topic. But actually there's a lot to learn about the details of this approach, up to the fact that, for example, there is an algorithm that does this, which is called fast Fourier transform, which is also a function implemented in MATLAB or other softwares. And if you know this, and then somebody, so if you know only this, and somebody says now use the fast Fourier transform algorithm in MATLAB, you will be fairly confused, because you get complex numbers out of it. There are no frequencies to be found. You have coefficients that are double, and it's all very confusing. So the thing is that there are a lot of details that we have to talk about. Good. Then we need, before we can talk about the first thing that is important for Fourier analysis, namely generalized cosine and sine functions, we need to briefly talk about the sine and cosine functions. And while we're at it, we also talk about the exponential function, because later when we look at different representations of sine and cosine functions, we use the complex exponential functions, so it makes sense to look at the exponential function at this point as well. So the second thing to talk about are the exponential function, the cosine function, and the sine function. So these are all functions that you have seen in school, so there's nothing really novel. So maybe I start with the picture for the exponential function. That's maybe the easiest. So this is an x-axis and this is a y-axis, a little bit tilted. So let's call this fx. Then the exponential function, if you plot it, if you have 0 here, this goes up to plus, or almost to plus infinity. This is negative here, and of course here it's also negative. So it's a typical thing like you've always seen, so let's not get with too much on the infinity here. So maybe just simpler, because we also need it. Yeah, we need the 1 at least, and 2 minus 1 minus 2 minus 1 minus 2. So it's a thing that you've seen many times in school. If you plot the exponential function, so you evaluate the exponential function, for this what you will get is a graph, which is also plotted here. There's essentially a number of features that are interesting about this graph. So first of all, if you put in x negative or positive, the exponential always comes out positive. So you can always use the exponential function to turn everything into positive numbers. If you put in 0 into the exponential function, you get 1. If you put in 1 into the exponential function, you get out what is called Euler's number, which is 2.71. So that's roughly here. And basically, based on this, you can already kind of sketch the exponential function. So that's roughly the exponential function, or let's say the graph of the exponential function. The way I write that here is that it's a function from the real numbers into the real numbers. You can actually say that's only into the positive real numbers, but the positive real numbers are a subpart of the real numbers. The important thing is you put a scalar argument in, you get a scalar argument out, univariate real valued function. It maps the axis onto x. Especially when I'm doing probabilistic modeling, I somehow prefer this writing of the exponential function, because that's how you see it most of the time in the Gaussian. You may have seen it, and also if one does Fourier analysis, let's do it like this. you might have seen it as e to the power of x, where e is then interpreted as Euler's number, whatever. So the real definition of the exponential function is actually the following. It is defined as a series from 0 to infinity xn divided by n factorial. So this is a series. A series is, if you want, an infinite sum. So recall the sum symbol. So if you have something like this, xi, this means x1 plus x2 plus x3. And here you now have a sum over n. So this is my n. Get a little bit used to my n. It looks like a u or something, but that's an n. N from 0 to infinity. And for each x that you put in, you have to sum up this x that you put in to the power of n divided by the factorial of n. So factorial of n, so for example 3 factorial being 1 times 2 times 3. And evaluate this infinite sum then. So this is not a trivial thing, and of course you will not do that manually. So if I write that out, it looks a little bit like this. So x to the power of 0 is 1 factorial 0 is also 1 by definition. So the first term is 1. Then x to the power of 1 is 1 factorial 1 factorial 1 is 1. So you get x, and then you get to these higher orders. So you get these, and so on to infinity for every x that you put in. Again, it might be easier to think of the exponential function like this. So what actually comes out of the series is for the values of x that I put in is what is plotted in blue here. So series are actually not that trivial mathematical objects. So the one question is whether they actually converge and whether this sum expression that is written here actually corresponds to a finite number and so on. There's a little bit on series and sequences in the handout or in the book. It's not horribly important. What will be important is that you appreciate that this is the definition, because this we really need to understand the complex exponential and its relation to the sine and cosine later on. Yeah, so it's more really to be okay with it that this is the definition, rather than now trying to compute it. I mean, you can try. I mean, put in x2 and evaluate the series for, I don't know, 10 terms and check whether that gives you the same as the exponential function from your calculator. Then you have definitely done something. But yeah, also don't be horribly worried about it. So as for the exponential function, we actually don't need many of these properties for Fourier analysis, so we also don't really need to discuss them. One thing that you might remember from school is that the derivative of the exponential function, as we talked about derivatives last time, is the exponential function again. So that's helpful. But of course, this also needs to, if you really want to talk about it, needs to be proven. Okay, I think that's as much as I want to say about the exponential function right now. Are there questions about this aspect of the exponential function? These aspects? No. Good. Then let's, the exponential function we will actually need once we have established the cosine and sine representation of Fourier analysis. So let's briefly look into cosine and sine now. So the cosine function is a function that takes in, again, scalar numbers and gives you values in the interval -1 to 1. And it is defined, again, by a series, namely the following. So if you compare that to what you've just seen for the exponential function, the series doesn't look that different. I mean, it still is a series. It goes from n to infinity. The x goes in, the x is taken to a power, and it's divided by a factorial. And you have, in addition, you have this factor here. Of course, you will be familiar with the cosine more from the trigonometric perspective. So does anyone remember how you evaluated cosine in school? With angles and stuff. So what was it? There was a formula. The cosine of the angle is divided by. Yeah, I think that's it, right? Gegenkathete durch Ankathete, durch Hypotenuse. Ankathete durch Hypotenuse. Yeah, one of them. Yeah. This is definitely not the geometric perspective on the cosine function. And the reason why we don't need this geometric perspective for the Fourier stuff. What we actually should keep in mind is how the cosine looks. So if you have 0 here, then a typical thing to plot the cosine over is to actually structure the real numbers in terms of multiples of pi. And then the cosine of 0 is 1. And then it does a full revolution over 2 pi. Now this will be fun. So this is, I make it smaller, it's easier for me. And this is pi half. This is 3 half pi, half pipe. So you go down here, no, almost, let's make this blue. No, it's not awesome, but it kind of is okay. So of course the cosine goes on, it doesn't stop here, but then does its thing again. But the important thing is that it does a full revolution, so going from 1 to -1 and back to 1 every 2 pi. And it starts at 1 for 0. Then there's the sine function, which is quite similar, as you all know. In terms of its series representation, it's also quite similar actually. So it basically, you can interpret this as the even numbers. So whenever you multiply a natural number by 2, or natural number and 0, by 2, you get an even number. So if you have 1 times 2, you get 2. If you have 7 times 2, you get 14. And the difference between the cosine and the sine in this representation is that for the sine, you actually take the odd numbers. So you take every n times 2, which gives you an even number, and then you add something, and you add 1, so you get always one more than an even number, which is always an odd number. And this is how then the series representation of the sine looks. And then, of course, you know that the sine and the cosine are essentially the same thing, but the sine starts at 0 and also then goes back to 0. Yeah, so they are shifted by pi half. Yeah. So that's sine and cosine function. So you have seen all of this before. The the new thing was the series definition. Again, we will need that. One thing we will also need actually is the derivatives of sine and cosine functions. So you also remember that the derivative of the sine function is the cosine function, and the derivative of the cosine function is minus the sine function. Yeah. So from a mathematical perspective, of course, this all would need to be proven based on the definition. But on the other hand, from school, you know that the derivative of sine is cosine, and the derivative of cosine is minus sine, and it was never really proven there, so why prove it now? It's just like 1 and 1 is 2. You don't need Peter Scholze to know that. Okay. Yeah, these functions are periodic, so maybe we need that. So if you put in x plus 2 pi into the cosine, what you get out is the value you have at x. Yeah, so for all x's that you put in, and the same applies to the sine. And what else do we need? Yeah, I guess we will need these addition theorems at one point. But maybe I just pull them out of the head once we need them, because then it's, yeah, well, it's whether I pull them out of the head now or then. Okay, so these are three functions, three univariate real-valued functions that will feature extensively in Fourier analysis, especially the sine and the cosine function. The exponential function will also feature when we talk about the complex form of the Fourier series. The exponential function is also, of course, quite popular in probabilistic modeling if you think about probability density functions. So the exponential, from my perspective, is actually around more than the sine and cosine, but in Fourier analysis, sine and cosine are, of course, very prominent. Good. So maybe as a last thing then for the first hour today, I now tell you what I mean by generalized sine and cosine functions, because these are the elementary building blocks of Fourier analysis. So what we discussed above are the cosine and the sine function. And the cosine and the sine function always, in their values, vary between -1 and 1. Always repeat themselves every 2 pi. And always for the cosine start at 1 for 0, and for the sine start at 0 for 0. Now the elementary building blocks of Fourier series are not the cosine and the sine function, but what I call the generalized cosine and sine function. And these are defined as follows. So the generalized cosine function is a function that takes in real numbers and returns values in an interval -a, and is defined as the scalar multiple of the cosine function. And as input, it's not x only, but it's 2 pi omega x minus phi. Yeah, so here you have something like an amplitude factor. Here you have something like a frequency not frequency factor, but frequency term. And here you have something like a phase term. What and why these things are called that, that's actually what I want to then explain after the first break. But before the first break, this I call the generalized cosine function, and of course similarly one can define a generalized sine function. Here with a b that multiplies the sine, and then a 2 pi omega x, which again refers to something like frequency, and a phase term for which I use the other phi just because. Yeah. So these two are the generalized cosine and sine functions, and well, maybe before we will talk in more detail about them, because for me and often you find that in presentation it's like, oh, that's it. But for me, for a long time it wasn't quite clear what this 2 pi omega actually is about. Before we talk about that in a little bit of detail, let me tell you actually the first big thing that we want to get to, namely linear combinations of those. So what we actually want to get at is to describe functions f, now it's a different f than the one above, functions f in the following form. We want to make sums here from k to n minus 1 of these generalized cosine and sine function, where we multiply each cosine with a different amplitude factor, ak. So this k depends on the iteration variable of the sum. So it goes k0, k equals 1, k equals 2, and so on, up to n minus 1. And the cosine also has a k-specific frequency term. And actually I'm omitting the phase term here. So I set the phase term 0 plus bk sine 2 pi omega k. Yeah, so this is what we want to get at. This is fairly close what is actually called the real Fourier series, although that's not quite the Fourier series, because this is just a linear combination, so a sum of weighted generalized cosine and sine functions. But this is where we want to get it. Yeah? So this is kind of the first, even before the real Fourier series, the first crucial thing to understand. But to actually understand this expression, we should talk a little bit about actually these things in there, namely the generalized cosine and the generalized sine function. And this is what we do after the break. Are there questions so far? Yeah.
Why don't we need the phase variable in the sum function?
Why do we need, or why we don't need? Actually here, so the story here is that I define it like that to show you some examples. One could put in some phase terms in here, but I don't want to.
Isn't there an x at this b times sinus 2 pi omega stuff? Yeah.
Yes.
And the sine function, the phase factor, is that also pi? Or?
Yeah. So these two. So this is var phi. So that's the phi variant, and this is the normal phi.
Oh, okay.
Yeah. Any other questions? No. Good. Then let's have a break and start at 9 again.